Welcome to a brief review of statistical concepts. This is just a brief review again of some basic statistical concepts that you'll need to have a firm grasp of as we move more in depth to data analysis. So what we're going to look at in depth is we're going to look at the different types of variables, independent, dependent, extraneous, the level that variables can be measured at and how confusing sometimes that can be. We're going to look at the theoretical normal bell curve and how we use that to help us interpret our data, as well as dispersion, which includes standard deviation. And we will look at how all of these come together to help us make sense of our data. We use data to tell our stories. And so the statistics really is just a tool to be able to tell our stories about the clients that we're working with or we want to work with or the populations we work with. So we're just going to do a down and dirty on some basic concepts in this presentation. So first of all, we're going to think about variables. And a variable is going to be anything that can change or be changed. So oftentimes in the work that we do in social behavioral sciences, the variable tends to become the treatment in which we're using with our clients. But anything that can change or be changed or be manipulated can be considered a variable. If it doesn't change, it's not a variable. So the example I use here is eye color. Can it be a variable? Now, genetically, my eyes are green, so they can't be changed biologically. I can change colors if I wanted to use colored contacts, so I can manipulate it in that way. And I could even engage in some type of experiment by manipulating my eye color and how people react to individuals with green eyes versus how people react to individuals with blue eyes. Even eye color, when it's a constant like that in our biology, can still become a variable because we can manipulate it. If you actually in your sample specifically select females who have blue eyes, then the attribute blue eyes ceases to become a variable. It's now a constant because it's not going to change on any factor. Everybody has blue eyes, so that's a constant. It's all going to be the same. And as we get more in depth into like multivariate analysis and factorial analysis, there are some variables that we want to hold as a constant. And so we'll learn some statistical procedures for doing that. But that's the simplest way to understand it, is if for whatever reason your sample consists of females with blue eyes, then gender ceases to become a variable. Everybody in the sample is the same, and eye color ceases to become a variable. So the variables must change or there's no opportunity for variance to explore. So if for any reason you don't set out to do this, but then you find out that your sample population is skewed towards, say, gender, then it'll become a constant. This actually happened in terms of my dissertation. My dissertation many, many years ago was on stress that family caregivers experience after placing a loved one in a nursing home. I had 16 different nursing homes, and so I had a POSIF sampling design. And it turned out when I got all my data in my analysis that 97% of my participants were female. I didn't intend on that, but all of a sudden it became a constant. It's no longer a variable. It's not large enough differences between male and females to demonstrate variance on any one factor. So when you think about your variables, they have to be able to change. And there may be some times when purposefully you make it a constant, or there may be sometimes that just due to the sampling procedure, it ends up being a constant and no longer a variable. Then we determine independent, dependent, extraneous variables. Of course, the independent variable is one that is manipulated or changed and is assumed to have the direct effect on the dependent variable. One easy way, in our work, because oftentimes what we're evaluating our treatment effects on our clients, is if you're measuring a treatment, it's always the independent variable, always. Because if you're adjusting depression levels or looking to treat depression levels, then depression levels are going to become dependent upon the treatment. And that's a way to think about the independent and the dependent variables. An example that I've written here is that students graduating from magnet high schools for science will have higher levels of science identity than students graduating from public high schools. If you actually break down this hypothesis, Students are our population. However we want to define those students, whether it be middle school or whether it be females or whatever, then our independent variable is going to technically be our intervention. Did they attend a magnet high school, or did they graduate from a public high school? So that's the intervention, and our dependent variable is going to be their level of science identity. And because sometimes it can be tricky identifying the independent variable, I switched this around just a little bit for you. So in this example, students graduating from magnet high schools for science will have higher levels of science identity than students graduating from public high schools. So our sample population again is students from specific schools, the independent variable, again, high school, magnet versus public, the dependent variable, science identity. But if now we say students with a high science identity will be more likely to choose to attend a magnet school for science than a public high school, our sample population stays the same, students. Our independent variable becomes science identity, and then their choice in high school. So what we're saying now is based on their level of science identity, it's going to influence what type of school they choose to attend. So this changes the independent and dependent variable depending on how the statement is written. In the research process, and it doesn't matter whether we're evaluating a treatment, whether we're actually doing academic level research, program evaluation, the research question and the research hypothesis becomes so important, and because depending on how they're worded is what we need to investigate. And so this is just one example of how you can actually take variables of science identity and type of school, and you can change them from dependent to independent. So it really comes to semantics almost, and I know in my experience when I'm writing research proposals and research studies, sometimes it takes me 2 or 3 shots to get the research question and the research hypothesis accurate so that I'm actually investigating what I'm intending on investigating. Again, these can become a little bit quirky, and when you're reading published research articles, especially if they're really complicated, and I don't know why we have to make them so complicated, but if they are, sometimes it's very difficult to determine exactly what they're exploring. And I've been through articles sometimes where I've actually had to just pull out information and write it down to try to figure out what they're doing there. Rule of thumb, I have to read a research article 3 times to try to understand it. I tend to toss it and get a different one. So anyway, this is just an example of how independent dependent variables can change depending upon what you're choosing to study. The extraneous variables are actually everything else. They're anything that could potentially affect the results of your study. You know, our goal of research, and whether we're doing experimental research, true gold standard experimental research with control groups and intervention groups, you know, the goal is we want to develop a research process we can say with high credibility and high certainty that our independent variable is in fact impacting our dependent variable. So we have all these extraneous variables that we have to account for, and that can be gender, socioeconomic status, parental education, parental attitudes towards science. All of these could also be impacting the student's science identity and their choice of school. I have to develop some way to explain these away. Either they're influencing it or they're not. So I collect additional information and additional data to run additional analysis, which could also include multiple regression, ANOVA, those different things, to find out if these other variables are in fact impacting my dependent variable. So the extraneous variables are everything else out there. We can never account for 100% of the extraneous variables. We can never say with 100% certainty that this treatment is reducing depression to this level. But the better we can construct our studies and the better our analysis is and our variables are and our data is, with more confidence we can say this treatment that we're using is having this strong of impact. And that's what we're shooting for here. We want to eliminate as much uncertainty as possible when we're engaging in positivist or quantitative type of research. So therefore, we're looking for a good model fit. And that's where we get a good model fit, then we have the ability of our model to reproduce the data. And so that helps explain those relationships. So if our model says that the CBT format that we're using to reduce depression in our clients is a good fit, then every time we introduce that, we're going to be able to reproduce the same data to show that it is. So we're looking for a good model fit in our data to be able to explain our independent and dependent variable relationship at a high level. It's also important to be able to recognize at what level the variables are being measured at. And again, this can be a little bit tricky in what we're doing. There's 4 levels. There's a nominal, there's ordinal, there's interval, and there's ratio. When we talk about nominal level, it's simply just what it is, nominal level. Is it gender, race, ethnicity, political party affiliation? Typically, these actually have words associated with them, and so not numbers. Now, a number in terms of data may represent it, like 1 may be Republican, 2 may be Democratic, but the numbers don't mean anything. It's the words that mean something when we're looking at nominal level variables. And one thing that we could do in terms of this is say, do you believe marriage impacts mental health? Yes or no? We've just created a question that produces nominal level data, a yes or a no. The next level is ordinal, and it actually indicates ranking. And then the best reflection of ordinal level data is when we look at our Likert scales. Strongly disagree to strongly agree typically represents ordinal level data. If you take socioeconomic status and you actually put it into categories, so you have annual income 0 to 12,001, 12,002 to 24,000, 24,001 to 48,000. If you put them into categories, you can actually take socioeconomic status and you can also make it an ordinal level variable with some ranking. There's some higher and there's some lower amounts. So you have less than and you have greater than, and there's some meaningful terms in this. Pain scales, those with the little smiley faces, those can be ordinal. Satisfaction with services, again, disagree, disagree, those are ordinal. We could actually take our question that we asked at a nominal level and then we could ask it at a ordinal level. Do you believe that being married improves mental health? And what we would say is indicate your level of agreement with this statement. I believe being married improves mental health. Strongly agree to strongly disagree. Therefore, it becomes ordinal. It's no longer nominal. So this is a little bit finer tuned. There's some controversy about what you can do mathematically with an ordinal scale. Some of them, and if you have a scaled instrument that actually has been through psychometrics, it'll tell you what you can do with it. But there's some belief that if you collect categories that have 7, at least 7, 1 through 7, that you can do some higher level statistical analysis with it. And then there's others who believe that it really strictly is ordinal and you're going to fall back into more of the nominal level statistical analysis that you can do. Then we have interval. And interval is specific because the numbers represent real numbers and there's real differences in the numbers. So interval variables, one value is not just higher than a number, but the difference between the intervals. This is where I like to say the numbers mean the number. If you're asking age, what is your age? You're asking it at an interval level. Simply because we can't be on Earth without some level of age, so there's not an absence of a 0. We can use our marital scale, again, our marital question, change it to an interval level where we could say ratings on a marital scale for mental health that has 10 questions. On the scale from 1 to 10, participants rate the impact they believe marriage has on different attributes of mental health, so they can have a collective score of 10 to 100, and this is going to make this an interval scale. So we went from asking, do you believe marriage improves mental health? Yes or no, that's nominal level. To indicate your level of agreement with the following statement. I believe marriage impacts mental health in a positive way. Strongly disagree to strongly agree. So now we can actually have 10 questions and have them rated on a scale from 1 to 10 in terms of how they believe mental health is impacted by marriage, and then we would have a composite score, and that makes this interval because there has to be a score between 10 and 100. We could say higher levels mean that they perceive higher mental health. So the mental health scale can become an independent variable, if we're exploring the hypothesis, women who score higher on the marital mental health scale will score lower on the depression inventory. So now we can take it and we can actually plug it into whether it's going to be an independent or dependent variable. Ratio is essentially the same as interval. The number means the number. You can actually do statistical and mathematical computations with it. The only difference between ratio level and interval level is in ratio there's a true 0 point. And this allows you to compute meaningful ratios because there's a true 0 point. In social behavioral sciences, we typically treat interval ratio as the same. So we recognize that ratio is the highest level. There's a true 0 point, which means you can have accurate ratios with that. But in our statistical analysis, we treat these as the same. If you're going to do a lot of the statistical tests, whether it be t-test, ANOVA, multiple regression, all of those, you're going to have variables that are going to be at an interval ratio level because the formulas typically require a mean. And you have to be able to get the mean, which we know as the average, but the mean to plug into those formulas. So that's why you have to have these variables at these levels to do a lot of the statistical tests. Understanding what level you're variable at is very, very important because that tells you what statistical test you can run that will have meaning. So this slide breaks it down and shows you the differences between the variables. So have you published research articles in a peer-reviewed journal? Those of you who are going to be entering into academia will know how important this question becomes. So at this one, we actually have a yes or no response. It's nominal. Then we're going to have a question. I have published a sufficient number of articles in peer-reviewed journals to earn tenure. Please indicate your level of agreement with that statement. We're going to have a range from strongly disagree to strongly agree. This is ordinal. Then we can ask, how many articles have you published in peer-reviewed journals? Okay. This can be ratio because there can be an absolute 0 here. I have published 0. Which means that we can then say Bob published 50% more than Jane published in 2020. We can actually have accurate ratio relationships. But again, we're going to treat interval ratio level variables the same in our statistical analysis because it has to do with the formulas that we use to calculate our statistics, t-test, ANOVA, multiple regression. So here we show the mean, which is the average scores. We know this is average, but in statistics, we reference it as the mean. And again, it's all the scores added up divided by the number of scores. We have the median, and that's the middle score. 50% is above, 50% is below. And then we have the mode, which is the most frequently occurring score. So collectively, these are our measures of central tendency. If you look down here at the bottom, I've kind of put in what we can do. If you have a nominal level variable, you're actually going to be able to report the mode. That's all you're going to be able to report if your variable level is nominal. If you have an ordinal level variable, you're going to be able to report the mode. It's questionable about the median and it's questionable about the mean from a statistical perspective as to what you're allowed to do with an ordinal level variable. We can play around with that this semester. At the interval ratio level, you can report the mode, but typically that's not a meaningful way to do it. The median is meaningful and the mean is meaningful. When we choose between reporting median and mean, we want to look at our mean to determine if there's skewness, and we're going to talk about some skewness with the bell curve. And an example of this is if you know in the United States, we typically report median household income. We don't report the means. We report median household income. And that's because there's fewer people in the United States who control much more of the wealth. So it skews the mean to show that we have a higher household income in the United States than we actually do. So that's why in the United States we report median. 50% of the people will earn an annual household income of this much, 50% will earn an annual household income below this much. That has much more meaning when we report our findings. Now, in terms of conducting statistical analysis, again, we need that level, that mean level, if at all possible, for most of our inferential statistical tests. So anytime you're designing a research study, anytime that you are creating some form of measurement tool, you want to try to capture data at an interval ratio level. So that way you can do the most statistical analysis with it as possible. If you don't capture it at that level, it limits the statistical analysis you can do. If you capture data at an interval ratio level and there's not enough variance or there's not enough what you need to run, you can actually bring that down to a nominal and ordinal level, and we can talk about how to do that. And one way that I typically do that is if I have an interval ratio level and I don't have a whole lot of, well, let me use this example. If I have an ordinal level, strongly disagree to strongly agree, and I don't have a lot of variance in there, either most people said agree or disagree, I will take that and I will collapse that down into two categories, agree, disagree, because it has more meaning. So I've taken ordinal and brought it down to nominal. If I capture data at an ordinal level, though, I can't explode it back up into interval ratio because I don't know what individuals had responded. They just fall into categories. So always, if you can, always capture your data at an interval ratio level because you can always move it back down to the nominal ordinal level, but you can't take nominal ordinal level and explode it back up into interval ratio. Okay, we're going to just take a look at the normal distribution, the bell curve, because this is a theoretical distribution that we use as a tool to help us understand the data that we have and where our data falls in terms of, I guess, what we're going to define as normal in our society. So the basic properties of the bell curve is the mean, the median, and the mode are all equal. The curve is symmetric, so at the center, meaning around the mean. Okay, so everything's symmetric. This is the perfect, if you will, theoretical distribution. Exactly half of the values are to the left of the center and exactly half of the values are to the right of the center. And the total area under the curve will equal 1. So the total area under the curve equals 1. So if we look at it here, for the standard normal distribution, there's a mean of 0 and a standard deviation of 1. And what that means is that the standard deviation right there of 1 on either side, you have 68% of the sample or the population are going to fall within 1 standard deviation of the mean, and then you have 2 standard deviations of the mean, and then you have 3 standard deviations of the mean. Okay, 95% of people or participants, or however you define that population, is going to fall within 2 standard deviations of the mean, and ideally 100% are going to fall within the 3 standard deviations of the mean. So this tells us where our sample falls based on this normal theoretical curve. Now, we can standardize, we can use the normal distribution of Z, and sometimes we're going to take our data and we're going to change it to the Z scores because this standardizes variables that may not fit into this normal distribution. We'll examine that more when we look at profile analysis, when we might have to change some of our measurement scores to a Z-score to standardize them so that they will match all of our measurement levels or scores, if you will. Again, in the theoretical distribution of the bell curve, the mean, the median, and the mode is all right there in the middle. They're all right there the same. If we get skewness, then we can have left skewed, so our numbers are going to be skewed towards the negative side of the curve. If we get right skewness, it's going to be skewed towards the positive side of the curve. So we're going to have, it's going to be rare, very rare, that you're ever going to have the perfect or close to the theoretical curve. We're going to tend to have some type of skewness in our data. The mean, like I indicated, if we use the mean, a lot of times this will skew our data. An example of this, and when we clean up our data, we'll talk about cleaning up data, we have to look at this. And an example of this, again, back in my dissertation, one of the questions that I asked respondents was how far away they lived from the nursing home. Median was like 30 miles, 50% lived 30 miles, more than 30 miles, 50% lived less than 30 miles. But I had a really strange mean. And when I looked at my standard deviation, which is dispersion, my standard deviation was really high. But when I went back and I looked at the respondents, because I just asked them the number of miles, so it's interval ratio level, I had one respondent that lived 1,000 miles away from the nursing home. Everybody else was clustered within a 50-mile range of the nursing home, if you will. This one lived 1,000 miles away. So it was positively skewing my data to this right-sided skewness here, and I had to decide what to do with that. When you have outliers, you have to decide how much they're impacting your data and what to do with that. In this particular situation, because I only had one that was that level of an outlier that was really skewing my data, I opted to drop them from the study. Again, you can't just drop them on the one variable. You have to drop them. You have to drop the participant altogether. If you have several that are skewing, you don't want to lose those participants, so you have to make a decision about what to do with that data. And again, there's some statistical procedures that can happen that will help with some of this if it's too skewed. But we have to know if it's positively skewed or if it's negatively skewed. So that means it doesn't fit the exact normal theoretical bell curve. It's going to be to one side. The mean, again, the mean is the one that's most effective by outliers and will give you your skewness. When we talk about dispersion, this is a tool that we use in statistical analysis to help us describe the spread of our data, again, around these measures of central tendency. I included range here. It's actually, the range is actually not the true dispersion. It's not considered one of the dispersions, but so the range fits into descriptive statistics. Because it informs us of things, but it doesn't fit into measures of central tendency, and it doesn't truly fit into what they define as dispersion, but I fit it here. So you can have a range of scores, and so we have scores examples here is 5, 3, 2, 5, 5. Our range of scores is from 5 to 2, so the range is 3. Typically, this becomes important, again, if you're looking at those outliers. And so if you end up with large outliers, it's going to give you a higher standard deviation, and you're going to be able to see where your range is. An example is we like to report our range, especially if we're looking at age. So maybe the mean age for your population is 63, and you have a range from 19 to 75. And this gives the reader the understanding that there's a wide range here, and even though your mean is 63, you have a lot of younger people included. So again, this is just a tool that helps us tell our story about the populations that we're looking at and how our data centers around those measures of central tendency within that theoretical curve. So like I've indicated, one way of describing how spread out the set of data is when the data has a large value, the values are widely scattered, or when it is in small items that are tightly clustered. So in the first one, we have the 1, 2, 2, 3, 3, 4. We have really tightly clustered data. So this is going to be a smaller dispersion value. It's going to center more around that mean, that median, that mode. It's going to be tighter, closer into that middle of the theoretical curve. Or we could have larger values. And so we have 0, 1, 20, 30, 40, up to 100. This is a big dispersion. This is a widely scattered plot, so they don't necessarily correlate around the mean. Again, going back, depending upon what your research question is, depending upon what your hypothesis is to how this will have meaning, whether it's important that they do cluster around the mean or whether it's important that they don't cluster around that. The interpretation will depend upon what you're investigating, okay? And one way to actually look at this is not only with the data there, but this is how you often use graphs through the SPSS, your dot plots, your box plots, your stem and leaves, because you can visually see the spread, and you can even overput on your tables, the theoretical curve and some things like that. So it'll give you a visual of what to look at, including looking at your standard deviation, your variance, your interquartile range. Again, these are all tools that we use to interpret our data to be able to tell our story. Standard deviation is one of the most common measures of dispersion that is reported. Anytime in statistics that you report a mean, you must report the standard deviation. You must. That's the accepted, that's the way it is. So when you have your data and you're writing up your report and you're going to give the mean age of 63, standard deviation of 12. you have to report that. That's the acceptable strategy. And that's because, again, that standard deviation tells us how tightly the data is dispersed around that particular mean. So it's always important to know the standard deviation. And so, and that standard deviation, again, is going to go back to that theoretical curve. Typically, how many standard deviations are they going to be away? And you may actually have to convert to z-scores to get that. But eventually you'll get to the point where you'll be able to look at your data and you'll be able to analyze it and know, okay, this is where I'm at in terms of the skewness, the standard deviations, and all of that. But it's important, again, anytime you report your mean, you have to report your standard deviation. Variance is the other common dispersion that you'll often see reported. And it's actually the average amount of error between the means and the participant scores in a sample. And this is how you get the variance. Of course, within your statistical programs, it computes it for you, but sometimes you need to understand how it gets it so you can understand what it means. So the total squared variance, which is the sum of squares divided by the number of scores, 1.6 units squared, but then you have to get rid of the squared. So the variance, and again, the statistical programs compute these for you, so you don't have to be as concerned about how you arrive at them other than understanding what they mean. So standard deviation and variance are the two most reported dispersion statistics used within what we do. And then this slide is going to show you the squared deviance. So when we added up the squared deviance, it becomes known as the sum of squares. So the total deviance of scores from the mean equals 8. And that's heavily influenced by the size of the sample. What we do know in statistics is that you can get a large enough sample, okay, that you're going to be able to show some level of significance, or if your sample size is too small, you may not show significance when there really is. These statistics, the standard deviation, the variance, all of that is going to be highly impacted by the size of the sample. So we're going to learn about how to engage in power analysis and look at effect sizes so that we can determine what our sample needs to be in order to have robust statistical analysis. So this was just a brief summary, again, of some of those key statistical concepts that'll be important to have a good understanding of as you're moving more in-depth to data analysis, into construction of measurement tools, into construction of research designs, programming practice evaluations. The next one, I've divided these up so they're not so long, but of course you can stop them and start them as you want to. But the next one, I'll go into more in depth about null hypothesis testing and how we use that in the social behavioral sciences. So I hope this was helpful, and you'll be ready to move on to the next presentation.